All right, we're going to continue on with these problems that I've clearly photocopied out of another book. Some of them are kind of challenging, or at least they're pretty involved, but we'll just take them step by step. They, in principle, use all the same ideas we were talking about in the videos for Chapter 8. First one, the moment of inertia of this wheel is given in SI units. We're given its radius, 0.4 meters. Find the angular acceleration of the wheel caused by the 10 kilogram mass if there's a frictional force between the 10 kilogram mass and the incline. So that means this thing's going to start falling down, and we want to know the angular acceleration of the wheel as this thing slides down and starts spinning the wheel. So we're going to do, let's take plus x to be down the plane because that's the direction this one's moving. F net x equals max for this one, and torque net equals I alpha. And if we're calling plus x down the plane, we better take positive rotations to be the direction this would rotate when the other mass moves down the plane. So counterclockwise direction is positive. And when we do that, let's see, in terms of the free body diagram for this, there's 4 forces on it. Tension force going up the plane, friction force going up the plane, weight force going straight down, and normal force perpendicular to the plane. So when we do F net x equals max, 3 of those 4 forces will contribute. Okay, so we do F net x equals max, and we can, since we're asked about the angular acceleration, we can exchange that ax for an alpha of the wheel because we know the tangential acceleration of the wheel is the same as the linear acceleration of this, and the tangential acceleration of the wheel is r times alpha. So this acceleration in F net equals ma can be replaced with the radius of the wheel times alpha of the wheel. Then separately I do torque net equals I alpha, and the torque is just the tension T in the string times the radius of the wheel. And that's equal to the moment of inertia of the wheel it's given times alpha. So those two equations will be in terms of the tension in the string and alpha, and we can solve for T equals and substitute into the other one for T, and we'll get an equation for alpha and then solve for alpha. That's how you approach this problem. 1183, frictional force between the block and the table is given. The moment of inertia of the wheel is given. How long will it take the block to drop 60 centimeters after the system is released? Again, the final question sounds like a kinematics question. If we only knew the acceleration of this, we could do a quick calculation in kinematics to figure out the answer to the question there. What we want to do is figure out the acceleration of this object, and we can do that by writing down 3 versions of F equals ma. We do F equals ma for, I guess we could call plus y down for this one, plus y to the right for this one, and positive rotations in to be counterclockwise for this one, so they're all consistent. F net equals ma y components, F net equals ma y components, torque net equals I alpha, where the net torque, let's see, if we're calling this direction positive, we would have, if we have the tension here T1 and T2 on the different sides of the pulleys, they're going to be different tensions because the pulley has a non-negligible moment of inertia. The net torque would be T1 times 0.3 meters minus T2 times 0.3 meters because they're pulling in opposite directions, so they're trying to twist it in opposite directions. That's equal to I times alpha, and we can replace alpha with A of this divided by R because the tangential acceleration of a point on the rim is equal to the linear acceleration of this one, and the tangential acceleration is equal to R times alpha. So solve for alpha there and plug that in terms of A. Now we're going to have 3 equations in terms of T1, T2, and A, and then we can solve for T1 equals, solve for T2 equals in the first 2 equations, plug those into the torque equals I alpha equation. We'll get one big equation that only has A as an unknown. Solve for A. Whew, that's a lot of work already. Now we got to use that to do a little kinematics calculation to see how long it takes to drop 0.6 meters. So that would be the y minus y0 is equal to vy0 times t plus 1/2 ay t squared. We just found ay, and vy0 is 0 because it's being released from rest. solve for t by taking a square root after solving there. 12.12. In figure 12.4, a uniform solid sphere is rolling on a horizontal surface at 20 meters per second. It then rolls up the incline and comes to rest at some height there where it stops, and the height above the earth is h. Friction losses are negligible. It looks like it's rolling without slipping, otherwise friction losses wouldn't be negligible. So let's use conservation of mechanical energy for the rotating case, and that means we'll take our system to be the ball plus earth. Gravity is an internal force. We can take the friction and the normal force to be external forces, but they don't do any work as this thing's rolling without slipping. That was discussed in the videos. So therefore, W net by external is 0, and that's equal to delta KE plus delta PE, and KE is 1/2 I omega squared plus 1/2 m v center of mass squared. And in this case, we know, in the final state, both omega and v center of mass will be 0 because it's come to rest. But initially, we know v center of mass is 20 meters per second, and the initial omega we can get from v center of mass equals r omega, which is one of our relationships for rolling without slipping. So that means we know kinetic energy final is 0, and kinetic energy initial has 2 terms that we need to include. And then change in potential energy is going to be the mass of the ball times g times h, right? Because delta y center of mass is h in this case. And then we can solve that equation, which is equal to 0 for h. 12.8. Here's a rigid rod joining 3 masses. This is actually quite a confusing problem. Well, I'll try to quickly talk through it, and if you want to worry about it, you can. If you don't, it probably will not hurt you at all, just because it's kind of symbolic and a little bit unlike any other problem we've done. So this rod has only 3 masses on it. The rest of the rod is supposed to be massless. The first thing I'm going to do is figure out where the center of mass of this rod is. If I call the pivot x equals 0, and this the plus x direction, we could find the x coordinate of the center of mass by doing, remember, the center of mass is m1 x1 plus m2 x2 plus m3 x3, all divided by the total mass. So this would be 2m times b plus 3m times 2b plus m times 3b. Divide that all by 6m, and whatever you get will be some multiple of b is going to be the center of mass relative to the pivot. I couldn't do that in my head, but it's somewhere out here, some multiple of b out here on the axis. We're going to need that in this problem because this bar is swinging down, and we need to know how far the center of mass goes down. So whatever the x-coordinate of the center of mass is, that's how far the center of mass falls on the way to the bottom. So we need to find the center of mass coordinate there. We also need to find the moment of inertia of this about the pivot point, so that we can use energy methods and 1/2 I omega squareds. The moment of inertia is, remember, the sum of m times r squared, where r is the mass of is the distance that bit of mass is from the pivot point. So in this case, we would have 2m times b squared plus 3m times parentheses 2b squared plus m times parentheses 3b squared. Okay, and we would add that all up, and we'll get some multiple of m times b squared. It's hard to know what it is, but that would be the moment of inertia of this object with respect to the point it's pivoted about. Then we're going to say initial is release from rest up here. Final is when it's zooming past this vertical position. And we'll say our system is the rod plus earth, with gravity being an internal force. We can take the pivot force to be external. The net work done by external forces will be 0 because the pivot force on the bar isn't moving. And in order for a force to do work, the point at which it's being applied has to move. So the net work by external forces is 0, and that's equal to delta KE plus delta PE. And delta KE in this case is just the change in 1/2 I omega squared. We don't use the 1/2 m v center mass squared in this case because The object is rotating around a fixed pivot. Remember, we only use the two kinetic energy terms added together, like in this case up here, where an object is rotating about its center of mass and its center of mass is moving. Here we've got an object rigidly rotating about a pivot, so we just use 1/2 I omega squared for K kinetic energy. And initial kinetic energy is 0, so we're going to have a 1/2 I omega final squared plus mg times delta y center of mass, and that will be minus the total m of this is 6m, and delta y center of mass, so it's going to have magnitude whatever it was the center, the x-coordinate of the center of mass of this was. So we put a minus sign out in front of that. That's the change in the potential energy. And then we can solve that equation for omega final. And if we know how, that tells us how fast this thing is moving, how fast it's rotating as it zooms across the bottom. If we want to find how fast the outer point is moving, we then need to use v equals r omega, and the relevant r there is 3v. So we multiply that omega final we found times 3v, and that would tell us how fast this little m is moving as it zooms past the bottom. Complicated problem and sort of unusual, so maybe I should have left that one off here. 1186, a uniform wheel of moment of inertia I, shown in this figure, pivoted on a horizontal axis through its center so that its plane, it's vertical, okay, and there's a small additional mass up here, and since this thing is pivoted, and if that little mass weren't there, it wouldn't tend to rotate one way or the other, but that additional mass over here is going to cause this thing to start rotating in the clockwise direction. So that small mass m is stuck on the rim of the wheel. Find the angular acceleration of the wheel when the mass is at point A. Repeat for points B and C. Find the angular acceleration of the wheel when the mass is at point A. Okay, so we could imagine. At first I was confused. That's why I was not saying anything for a second. I was confused because I was thinking, well, if I release it from rest here, that mass is never going to make it up to B. It doesn't matter. What the problem is asking, suppose doesn't matter how it gets to A. Suppose I move little m down to A and release it. What's the angular acceleration at that moment? That's what's being asked. Suppose I move the mass up to B. What's the angular acceleration at that moment? Well, that's pretty clearly going to be 0, right? If I move the little mass up here, it doesn't want to tend to rotate one direction or the other, so the angular acceleration at B will be 0. But what if I move the mass to C and release it? What's its angular acceleration there? And the idea is we're going to use torque net equals I alpha. The I for this is I guess just the symbol I here, so the moment of inertia of the wheel is I, plus it has an additional moment of inertia of little m times this radius r squared, and r is little b. So the moment of inertia is going to be I plus little m times little b squared, because we've got two different things contributing to the moment of inertia. So we use torque net. Torque net is going to be, well, let's see, if we're at A, torque net is going to be little m times g times b is the moment arm. So the magnitude of the angular acceleration will be gotten from torque net equals I alpha, where I has those two terms added together. Whereas the magnitude of torque net when the mass is at C, well, there its moment arm is only b times the cosine of 37, so it would be, its angular acceleration would be cut down relative to A by a factor of cosine of 37. And then at B, as we said, the angular acceleration would be 0. So you're going to solve torque net equals I alpha for alpha in those three cases. And in the second case, it's 0. 1187, a uniform thin rod, such as a meter stick, stands vertically on one end of the floor. Its top is now given a tiny push. So we imagine we try to balance it, but it's just a little bit off and it starts to topple over. Assume the base of the rod does not slip and find the angular acceleration of the rod when it makes an angle theta with the floor. and the tangential acceleration of the upper tip of the rod at that location. So let's first find the angular acceleration. We could use, initial will be when it's standing up vertically and it has no kinetic energy, and then final is when it's zooming past this configuration here where it makes an angle theta with the horizontal. And we're going to take our system to be the rod plus earth. Gravity is internal. We can take the pivot force to be external, but it doesn't do any work because the pivot point at which that force is being applied doesn't move. So W net by external is equal to 0. That's equal to delta KE plus delta PE. Delta KE is going to be 1/2 I omega final squared minus 1/2 I omega initial squared. Omega initial is 0. The I is, if I remember correctly, for a rod pivoted around one end is 1/3 ml squared, pivoted around one end. So we have 1/2 times 1/3 ml squared times omega final squared, plus the change in potential energy, and we have to say, how far does the center of mass of this rod fall on the way there? So it was a distance L over 2 up, and then now it's only L over 2 times the sine of theta, so it looks like it will be L over 2 times 1 minus sine of theta will give how far the center of mass falls down. L over 2 times 1 minus sine of theta, if I understood that correctly. That's how far it falls down. So then we have a minus m times g times L over 2 times 1, in parentheses, 1 minus sine of theta. Okay, set the sum of those things equal to 0 and solve for, I'm doing the wrong problem here. We're supposed to just find the angular acceleration. Okay, never mind. Scratch all what I said earlier, and let's just do torque net equals I alpha if we want to find the angular acceleration of the rod. We don't need to worry about how it started. It's all we care about is what it looks like right at this instant. So we're going to do torque net equals I alpha to calculate the torque. We will pretend that the entire gravitational force is concentrated at the center of mass, which is right at the middle of the meter stick, or stick, whatever it is. And so we will have torque net is mg times the moment arm, L times the cosine of theta. So mg times L over 2 times the cosine of theta, that's going to be the net torque, and that's equal to I, that's 1/3 ml squared, I think, times alpha, and then solve that equation for alpha. Then if we want at that same instant what the tangential acceleration of the upper tip of the rod is, we use A tangential equals R alpha, where R is equal to L. Solve for A tangential. Sorry about that initial misstart. I thought we were supposed to find something about how fast it's rotating. I didn't read the problem carefully enough. Okay, 12.9. When the system of figure 12.2, that's this one on the right, is released from rest, the 200-gram mass slides down the incline against a frictional force of 0.5 newtons. If the moment of inertia of the wheel is so big, how fast will the block be moving after it has slid 1 meter along the incline? So I would change this to, 0.2 grams, let's change everything to SI units just to be cautious there. How fast will the block be moving after it has slid 100 centimeters? So we've got the moment of inertia of the wheel. So what we're going to do is take our system to be the rotating disc plus this mass in combination with the Earth, and that gravitational force is going to be an internal force. Now this piece's center of mass is not falling, so we don't have to worry about it for the change in potential energy, but this one actually is falling as it goes down. So this one's going to go into the change in potential energy thing. And both of these are increasing their kinetic energy. This one has a 1/2 I omega squared kinetic energy. This one has a 1/2 mv squared kinetic energy. So system is these two masses plus Earth. You know, the normal force from the plane, the frictional force from the plane, and the the force from the pin at the center here we'll call external forces. The pin, I'm assuming this is a frictionless wheel here, but it says there is friction there. So that friction, as this mass falls, does some negative work. So if we do W net by external, that's going to be minus 0.5 newtons times 1 meter, if it moves 1 meter down the plane. That's the work done by friction, that negative work, is equal to delta Ke plus delta Pe. And delta Ke has two parts, right? This part has a 1/2 I omega final squared minus 1/2 I omega initial squared, and that's omega initial is 0. This part has a 1/2 mv final squared minus 1/2 mv initial squared, and v initial is 0. We can change out omega using v equals r omega to get omega is equal to v over r, because we're asked for how fast the block is moving, so we can exchange out the omega for v over r. And then for the change in potential energy, if this thing moves 1 meter down the plane, the amount of height it goes through is minus 1 meter times the cosine of 53 degrees. So we would have 0.2 kilograms times 9.8 times minus 1 times the cosine of 53. Whew. Okay, solve all that for V final, and we would figure out how fast this is moving when it gets down there. These are challenging problems, or at least they're somewhat involved. They're not, 1 or 2 steps and being done. Okay, a uniform 25 centimeter long stick rotates freely about a horizontal axis through one of its ends. It is released at an angle theta to the vertical. Okay, so we're looking at this figure over here. When it hangs straight down, the speed of the tip is 3 meters per second. How large is theta? So thetas are unknown here, and we are going to use conservation of mechanical energy between this initial state and the final state when it's zooming through the bottom. So let's take our system to be rod plus earth. Gravity is an internal force. We can take the pivot force on the rod to be external, but it's not going to do any work. W net by external is equal to 0. That's equal to delta Ke plus delta Pe. Delta Ke is 1/2 I omega squared. There's no V center of mass term in there because this is a rigid rotation about a fixed axis, so we just have the 1/2 I omega squared term. Of course, omega initial is 0. Omega final is, just 1/2 I omega final squared. So we can exchange out that omega final for the speed that's given using v equals r omega, where r is L in this case. So we would use v final is equal to L times omega final, so omega final is v over L. And then, so that puts it in there. Okay, so that's our delta Ke plus delta Pe. Let's see, how far does the center of mass go down? Well, it goes down a distance of, this is L over 2 times the cosine of theta plus an additional L over 2 as it goes down to the bottom here. So it would be L over 2 plus L over 2 cosine theta, that quantity with a minus sign times mg. Okay, put that in for the change in the potential energy. Solve all that. Well, let's see, I guess we know everything in that equation except the theta that came into that cosine of theta. So we could solve for cosine of theta and then eventually take the inverse cosine to figure out what theta is. 1122, a grindstone has a moment of inertia of so much. Constant torque is applied. The flywheel reaches an angular velocity of so many revolutions per minute in 15 seconds. Assuming it started from rest, find the angular acceleration and the net torque applied. The angle turned through in 15 seconds and the work done on the flywheel by the torque. So in this case, at least the first part of this sounds a lot like kinematics. Find the angular acceleration, so we can say, in this case, we know the time it takes to get up to a final speed. So we could say omega final equals omega initial plus alpha times t. Alpha is what we want to find out in A. We've got t, we've got our omega final. I would change this to radians per second just by multiplying by 2 pi radians is 1 revolution and 1 minute is 60 seconds. To change this to radians per second. Put that into that kinematics equation and solve for alpha. Omega initial is 0 in that case. So we've got alpha. Find B, find the net torque applied. So we would use torque net equals I alpha. We've got I here, and we know alpha, so we can solve for torque net. C, the angle turned through in 15 seconds. So it starts from rest. We want to know delta theta in going from rest to at the end of this 15 seconds. So there's several ways to do it, but we could use omega final squared equals omega initial squared plus 2 alpha times delta theta. We know alpha, we know omega final in SI units, we know omega initial is 0. Solve for delta theta, that would be in radians, and then we could convert it to revolutions by saying so many radians times 1 revolution divided by 2 pi radians would give us how many revolutions it goes through in those 15 seconds. Oh, I guess it's saying angle here, so it probably wants it in radians. D, the work done by the flywheel by the torque. Okay, so we can just we can say, look, this thing isn't changing potential energy at all because it's just spinning in place. Its center of mass isn't moving, so it's only changing kinetic energy, and that means the net work done by external forces, and the only external force doing work that's changing its kinetic energy is the torque on the flywheel. So the net work done by external forces is equal to the change in kinetic energy, and the change in kinetic energy is 1/2 I omega final squared. So put in omega final in radians per second and calculate 1/2 I omega final squared, and that will be equal to the net work done by all external forces, and it is the torque that's doing that, so that's the answer to D. Okay, 1123, a nearly massless rod is pivoted at one end so it can swing freely as a pendulum. Two masses, 2m and m, are attached to it at distances 3b and 3b respectively from the pivot. The rod is held horizontal and then released. Find its angular acceleration the instant it's released. So we're going to do torque net equals I alpha. We need to figure out where the center of mass is on this. So we have 2m and m at positions b and 3b. So if we want to find the x-coordinate of the center of mass when it's horizontal, I would calculate 2m times b plus m times 3b, all of that divided by the total mass, 3m, and figure out what fraction of b the center of mass is. And then and then when we calculate the torque we can assume the net force from gravity is being applied. We can assume it's being applied at the center of mass location. So the total mass 3m times g has a moment arm of whatever that x-coordinate of the center of mass was. That's going to give us our torque net, and we're going to set that equal to I times alpha. We want to find alpha, so we first got to find I for this. And I is going to be the sum of the m's times the r squared. So the I would be 2m times b squared plus m times, in parentheses, 3b squared, whatever that ends up being. So put that sum in for I, and then multiply that whole mess times alpha, and then solve for alpha. That would be the angular acceleration at the instant it's released. 1124, 3 children are sitting on a seesaw in such a way that it balances. Okay, we've got a 20 and 30 kilogram boy on opposite sides, equal distances from the pivot. A third boy who's also on there jumps off, thereby destroying the balance. So 3 boys are on it. We're told where 2 of them are, and the third one jumps off, and we want to know the initial angular acceleration while it's still horizontal. We're supposed to neglect the weight of the seesaw board. So in this case, if we, imagine the 30 kilogram boy on the right, 20 kilogram boy on the left, and we'll take clockwise rotations to be positive, then the net torque would be 30 times 9.8 times 2 meters minus 20 times 9.8 times 2 meters. That would be the net torque. We'll set that equal to I times alpha, and we want to find alpha. And remember, I is just the sum of the m's times r squared. So I would be 20 times 2 squared plus 30 times 2 squared. Whatever that number is, that's our I. And then solve for alpha, and torque net equals I alpha. 1125. A pendulum consists of a small mass at the end of a string of length L. The pendulum is pulled aside to an angle theta with the vertical end released. At the instant of release, use the suspension point as axis. Find the torque on the pendulum and the angular acceleration. I guess we're supposed to do this all in terms of L and theta. So the torque in this case is going to be, well, let's see. You got to visualize a little bit here or draw a diagram. The force is going to be little m times g, and its moment arm will, let's see, if it's pulled aside to an angle theta, its moment arm is going to be L times the sine of theta. L times the sine of theta, yes, gives the moment arm for the force. So the net torque, or the gravitational torque on it, is going to be little m times g times L sine theta. And its angular acceleration is got by using that torque equals I times alpha, where I, let's see, the string is massless. So I is just m times L squared. Remember, you sum up all the mr squareds. In this case, there's just one point mass. So the moment of inertia of this simple pendulum is m times L squared. So net torque equals ml squared times alpha. Solve for alpha to get the angular acceleration. 30. Constant horizontal force is of 1.2 newtons is applied tangentially to the shaft of a solid disc rotating about vertical axis. I'm not yes, okay, so we're saying that we're looking down from the sky in this case. In other words, the axis is coming out of the page, but it's going up vertically, so there's no gravitational kind of thing we need to worry about in this problem. The radius of the shaft is 3 centimeters, radius of the disc is 8 centimeters, its mass is 4 kilograms. Calculate the angular acceleration of the disc, ignoring the mass of the shaft. Okay, so what we need to do is calculate the net force on this, the net torque on this, and the only thing exerting a torque on it is the 1.2 newtons, which has a moment arm of 3 centimeters, or 0.03 meters. So 1.2 newtons times 0.03 meters is the net torque, and set that equal to I alpha. And here for I, we're going to use the moment of inertia of a uniform disk. Oh gosh, what is that? 1/2? I think it's 1/2 mr squared. So 1/2 times 4 kilograms times 0.08 squared, right? And that's the moment of inertia. Okay, and then set torque net equal to I times alpha, solve for alpha. Whew. That was a lot to talk through without having anything diagrams drawn, but hopefully that helped you, and maybe looking through the very terse solutions that the person who wrote this book, they actually put the solutions in, and I've scanned some of them down below. Maybe that discussion will help you pick your way through those solutions.